I would rather have it on Tuesday. I'm not so,
All right.
today we're not prepared for tomorrow.
All right, yeah, let's just take a vote because then we can see the silent, the silent majority. We want to make sure we don't miss them, right? But usually it's, the most vocal people are going to be heard, but we want to make sure it's fair, so. So we said, what did I just say? Who wants to take it tomorrow? Who wants to take it on Tuesday? All right, then that's it. So we'll just do it. I mean, maybe there are a lot of people who don't care. Tuesday or Thursday, doesn't matter. All right, let's continue. Were there any questions before we get started? Number 15 from what? The mock exam? All right, tell me what it said. 5 liters of blood. All right, I think I know what it is. Number 15. Was it 5 liters of blood? Blood contains iron 2, right? And so, what were the concentrations?
1.3 times 10 to the negative fifth.
Molar?
Yeah.
5 liters of blood, and then what else was added to that?
A drop.
Cyanide? Sodium cyanide? What was the concentration?
6 molar.
6.0 molar cyanide? Got it? And then the question is asking how much of the iron?
Yeah,
What percent of the iron is complex, or what percent remains?
Yeah.
What percent remains? All right, and so so we see this. You need some additional information. Iron 2 plus cyanide. Well, what does it form?
Ferrocyanide. Hexocyanide.
Hexocyanol,
Ferrite.
ferrate,
Mm-hmm.
2.
3.
Actually, it's got to be 2. Did I say 3?
That should be Fe3 plus, right?
Yeah.
Yeah.
Okay. What's a KF for this? 10 to the 10 to the positive 37?
Yes. Yeah.
Is only 10? There's no sig figs?
Yeah.
All right. So this hasn't been so accurately measured or precisely measured, so it doesn't have much sig figs. So this is not terribly reliable, this number, but it's okay because it's just huge. This number is huge. That means cyanide and iron 2 make a good match. And so this is we just set up our ACE table, and so initial is 1.3 times 10 to the minus 5 molar. Cyanide is 6. Actually, this is wrong. I can't do this because I have to look. Whenever we mix 2 solutions together, I have to do
Solution dilution.
solution dilution. So this is incorrect. I got to do my solution dilution. So what I'm going to do is I'm going to get 5. See, 1 drop is a tiny amount, so I'm going to, should I do this liters, or I'm going to do this milliliters. So I'm going to do 5,000.05 liters, because we're going to just assume a drop is around 0.05 liters. And so we need to calculate the new iron concentration here. Well, iron concentration is barely going to change because it's a 5,000 to 5,000.05 dilution. Times 1.3 times 10 to the minus 5 molar. Did somebody already calculate this? Somebody already have it calculated? Save some time.
It's 1.3 times 10 to the negative fifth.
Yeah, essentially it's going to be 1.2999999, which is going to be about 1.3 times 10 to the minus 5. Or- Is it? What does it come out to? All right, let's just use that. That's better.
Or 0.0001299987.
All right, point 4 zeros, 1, 2, 9, 9, 8. Smaller. All right, then the cyanide, so it barely changed. This is about 1.3 times 10 minus 5 molar. The cyanide is going to be a huge dilution, 0.05 over 5,000, 0.05 dilution of 6.0 molar, which is going to give us what? Zero point zero 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 zero. 4 zeros, 599.
Yeah.
Thank you. It's about 1,000 time dilution. 10,000 time dilution. Sorry. So these are our initial concentrations after solution dilution. So we just plug them in here. Point quadruple 0, 1299998 molar. Cyanide, point quadruple 0, 599 molar. Complex 0 molar. All right, which way is the change going to be here? How is the change going to go right? Yeah. But what would you do? Hopefully by now this is automatic. By chapter 18, if this isn't automatic, probably should go back, do some more review. But you should see this right away. We need to reset this. You know, a lot of people. Still by chapter 18 are still resisting this whole idea of reset. I'll find every semester. What's the limiting reagent? The cyanide or the iron? Actually, aren't they both 10 to the negative 5?
Yeah.
They're both 10 to the negative 5, so this particular problem, a lot of people, whatever, last semester, got this wrong because they couldn't figure out the limiting reagent. Limiting reagent should be like a Chem 1A, and I shouldn't even have to talk about the limiting reagent, right? I mean, you should be able to get the limiting reagent no problem by now, but it turns out, well, gosh, a lot of people got it wrong. A lot of people got it wrong, more than I expected, because it turns out the limiting reagent is not the iron. The limiting reagent was the cyanide. And so, it's too bad. A lot of people, not a lot, I mean, I'm talking like 10%. You wouldn't even expect 10% of Chem 1B students not to be able to get the limiting reagent. But this may be tricky because by sight it's hard, you know, when you're dealing with scientific notation and all this other stuff, you know. But in the end, what you should do is, if you don't see it right off and you aren't, you know, totally sure, then just do the calculation, Chem 1A style stoichiometry calculation, figure out what the limiting reagent is. And so this is what we call minus 6y, and therefore y is what? If I didn't round this, it'd be easy. I mean, if I just rounded this to 6, then it would be really easy. It'd just be 0.00001.
Yeah.
But since I rounded, since I'm carrying extra digits, we'll just calculate. What is y?
0.00.
3 more zeros,
3 more zeros,
9982.
9982. All right, and then can you do the subtraction here?
Point 5 zeros,
Okay,
3016.
3016. Okay. And this is gonna be 5 zeros, 9982 over here. All right, this is our reset, and then the change is gonna go backwards, so this is gonna be plus X molar. This is the other thing. A lot of people did this last semester. A lot of people didn't do the coefficient. What's the coefficient on cyanide? Coefficient 6. A lot of people just said plus X here because chapter 17 and chapter 16 it was all 1 to 1 to 1. And then all of a sudden we're back. Like this is like chapter 15 where we have coefficients that aren't equal to 1. So everybody got in the habit of just saying plus X, minus X. Right? But this is not plus X, this is plus X plus 6X. And so this was the other big mistake. So 2 big mistakes that happened on this problem. One, people got the limiting reagent wrong when they reset it. Oh, actually, the first mistake was some people didn't reset this. They weren't able to solve the math. Even they tried successive approximations, they still weren't able to solve the math. 2, the other issue was they got the limiting reagent mixed up. They did iron as a limiting reagent, which is weird because they would have gotten the negative molarity for cyanide how they did it, but they did it 1 to 1, everything 1 to 1 to 1, you know. And then people who did this right and then screwed it up here with this, doing plus X and minus X. But anyway, that was it. And then, you know, a small percentage had no idea where to start this problem, just left it blank, you know. And so that's 5 zeros, 3016 plus X, 6X. Five zeros, 9982 minus X. When programmable calculators were allowed, you know, that's when I had the greatest resistance to resetting. You know, when programmable calculators were allowed, a lot of people just said, oh, you know, I'm just going to use my equation solver. I don't care how bad the math is. The solver should be able to figure it out. And then I had to figure out how many digits does this programmable calculator carry, and it turns out, fortunately, it doesn't carry like hundreds of digits. Fortunately, it carries a limited number of digits. So all I had to do is figure out the change. I had to make the change 1 digit more than your calculator carries, so your calculator rounds it off to make it 100% change. And they ended up with 0 at the end. You end up with a 0. This is like, there's a question that was posted. You know, if it's a 100% change, the equilibrium is going to have a 0. And then when you double check your K, it's either going to be 0 or infinity. It's not going to work. You cannot have a 100% change. That's a hint for the other thing on Piazza that I noticed. It's wrong to think it's going to be 100%. Well, anyway, going back to this, let me just solve for X, right? I'm not going to finish this. I'll let you finish this because this is just algebra, right? And then once we get that, then the percent that remains is this concentration here. The percent remains is this divided by the original amount. The original amount was 0.00000 quadruple 0 129998 times 100%. So once we calculate this, I'll tell you though, since we reset this and the 10 to the 37th, the X is going to be minuscule. The simplifying assumption is going to work beautifully here. In fact, X is going to be so small that this is going to be about it. It's going to be very close to this number. Is that okay, or do you want me to solve the algebra? Okay, we'll skip the algebra. right, other questions? Uh-huh. Number 5, can you just read out the question?
I wish to dissolve the solid silver chloride.
Yeah, I think
The
it's-
solution containing
because
high
this is a
concentration of hydrogen attracted into the protocol.
Okay, I'm sorry, I couldn't hear it. Just one more time.
I wish to dissolve the solid containing.
Silver chloride?
Yeah.
Okay, which one is the best?
Yeah.
What were the choices?
Use liquid hydrogen.
All right, so silver chloride, which one is best for dissolving? And so the choices are hydronium?
Yeah.
Yeah,
just that.
hydrogen. Just hydrogen.
It will dissolve it.
Hmm?
It's asking if the hydrogen will dissolve it.
Will hydronium dissolve silver chloride?
Yeah.
Yeah, there's a high concentration of it would dissolve, silver chloride. Yes or no? Or true or false?
When we think about the solubility, we look at silver chloride solid, this goes to silver ions plus chloride ion.
Mhm.
So how does hydronium impact that? What does hydronium react with or interact with in this case? The only thing hydronium would do is cluster around chloride, but hydronium and chloride really don't react because chloride is too weak. And so we wouldn't form HCl molecules in this case.
Mhm.
And so the only thing is what we call the uncommon ion effect. You know, we expect a tiny increase, but nothing significant, so the answer is no. Pretty much it won't dissolve it. And so it's did I say it dissolves it? It will dissolve or it won't dissolve?
It's asking will it.
Will it dissolve?
Yeah,
Will it dissolve? No, it won't dissolve. It won't dissolve.
So this is what
And so the answer is no. It's no because it, the other thing is, you know, this is the way we handle it in Chem 1B. Do we see, are we gonna get some kind of Le Chatelier shift in the KSP? In Chem 1A, we would have done it like this. We pick any acid source, like nitric acid maybe, and we try it. Silver chloride plus nitric acid. This is just normal concentrations of nitric acid. And then we would get silver nitrate plus HCl. And we say that the leveling effect is, this is aqueous, and therefore there's no driving force for this. And so we get no reaction. Now, I told you silver chloride would dissolve in nitric acid, hot concentrated nitric acid. Do you remember that?
Mm-hmm.
Yeah, and so when we do the Chem 1A, this is in the PowerPoint. I don't know if anybody remembers the PowerPoint slide way back at the beginning where I said, do you guys remember this? I said that the concentrations, this is assuming the concentrations are 1 molar. You know, and then I said, in fact, this reaction is on that PowerPoint slide, but you know, I didn't put out all the products, and I think I even wrote the wrong products. You know, hot concentrated nitric acid is going to attack the chloride. I need to go back and fix that slide. But under normal conditions, the nitric won't do anything. This is under normal conditions, yeah. And also, it's hydronium. It's not an oxidizing acid. It's just some mineral acid we're talking about. Now, the situation is, if I wanted to get all fancy on you guys, and I wanted to really probe, you know, how well you understood this stuff, you know, I would have done this. I would have done this. I would have said, okay, now can you put 2 and 2 together, right? How well do you know what we talked about? Remember when I was talking about this whole thing about solid to solid conversion? Could you have seen that this is going to be a solid to solid conversion, and therefore, if I asked you, will it dissolve in HBr, you would have said yes. It will dissolve in HBr because what we're going to get is, we're going to convert the silver chloride into silver bromide. You know, and that's something you would be able to connect if you've seen it a bunch of times. I mean, I could then if I wanted to extend it further, like this is somebody who oh yeah, I saw this. We saw the silver chloride solid with competition with bromide. It's going to do this. But if I wanted to really see, you know, how well you understand chem, I might have done this, you know, with the HI and then see. What do you think? HI is less soluble, more soluble? What do you think? And so this you would have had to put together the hard, soft, acid base. Now I barely talked about that hard, soft, acid base, but I did give you clues already. I told you that if we did this purely electrostatic, right? If we did this purely electrostatic, then I would have predicted chloride would have been less soluble than bromide, but it turns out that bromide is less soluble than chloride, which means that covalent interactions are much more important, which means that bromide being a soft anion, that means silver's got to be soft, so it's got to be a soft side. And that means iodide is even softer, so it's probably going to be even less soluble, right? Something like that would be an extension. But the thing is, how do you do these extensions of knowledge is you have to have the basics really well down, and the basics you get by just repetition. You know, you repeatedly see it, and eventually you start to get bored. Oh, that's too easy. I got this down, and then you start thinking about, you know, how you can extend that. But most people, what I find is most people don't even have the basics down, and it's so easy to get the basics down if they just go back and just reread their notes over and over. I know it sounds. It doesn't sound so effective, but you know, I found it to be extremely effective. Just read it over and over and over again until you're bored with it. Then you start to when you get bored with it, that's when, you know, that's how they say the technology is expanded. They say, I was watching this documentary, this is a quick side topic, about some of these early chemical reactions that they did, like concrete and other stuff. And it turns out they were saying that, you know, all the hunter-gatherers, they're spending all their time looking for food. They didn't have time to get bored with things and start tinkering with things and start thinking about things. And so once they started the agriculture, then that opened up so much free time that people started tinkering with chemical reactions and trying different things. And that's how some, like the Romans, made tremendous advances in structural materials and architecture and whatever else, because they had the luxury of getting bored with things. By this repetition stuff. But anyway, getting back to this, you know. So, you know, a lot of people, they don't make the connection. So when they get a question like this, they say, hey, you know what, that was totally unfair. You know, that was nothing like you had, you know, on whatever in lecture or whatever else. But, you know, it's hard to make those connections until, you know, you make the neural connections in your brain. Okay, other questions?
Do you mind doing problem 9 really quickly?
What was 9?
Here it is.
Fully as you can. Turn off all lights and cover windows if it's possible. Silence your cell phones and take cover out of view. Shelter in place until you receive further notice from law enforcement or other emergency personnel. I repeat, this is a drill. It is a lockdown, shelter-in-place drill.
All right, so I'm supposed to attempt to lock the doors from the inside here, but those doors only lock from the outside. So we're supposed to make a barricade against the doors. So we would push all the desks against the doors or something, and then try to hide. But you know, we have an escape route here. Here, except this escape route is locked. So if I get shot or something, you grab the keys and then escape out that way.
We just have something.
So we'd go back there and then try to hide. But not every door, not every room can have that. So we'll see. All right, so we're supposed to turn off the lights for 15 minutes, but we already did the earthquake drill and this. So are we okay?
Yeah.
With this?
Yeah.
All right, so can somebody read off number 9?
Yeah, number 9.
So number 9 is a solution contains initial concentrations of 0.2 molar silver ion and 0.1 molar CO32 minus. Percent precipitation of silver ion will be what? And they give you the KSP for silver to carbonate, which is 8.5 times 10 to the negative 12.
So we're doing silver carbonate. So these are, okay.
In an emergency.
Attention, this is the El Camino College emergency broadcast from the incident commander at the El Camino Emergency Operations Center. This is a lockdown shelter-in-place drill. I repeat, this is a lockdown shelter-in-place drill. Building captains are to retrieve their emergency radio and direct your emergency building teams to take charge of your buildings. Secure all buildings and direct people in the hallways to seek shelter in the nearest safe classroom, office, or other room if you can. Shelter in place, remain silent, and stay where you are until you receive notification and or direction from law enforcement and or the El Camino College emergency response personnel. This is a shelter-in-place lockdown drill. I repeat, it's a drill.
Are the police gonna come by? Are they gonna check?
We could still see.
Yeah, because those doors, we can't lock those, and we're gonna go out this way. Can you unlock it? Or
Poor guy. Lockdown drill.
Wait, now you're gonna.
Narrow escape.
a 15 minutes of this, is that? But we'll probably do something with the doors or something in the meantime, but, I'll tell you, a lot of people, what they did with this problem is they included silver carbonate in the ice table. We don't, but in reality, it's there. It has to be there. This is why, Visual Mintech has the infinite solid. The infinite solid means you got plenty of solid there. If you don't have enough solid there, you can't reach equilibrium. And so we have infinite solid to make sure we can reach equilibrium. And the same thing for us here, because in this particular case, and I told you in chapter 18, we do a lot of what? If it's required, we're going to reset it. And so this case, I would just reset it again. Look at that K. And when we reset it, which one's the limiting reagent? Well, this one I tried to make easy because,
There is no limiting reagent.
yeah, so it's stoichiometric. So it goes 0 molar and 0 molar. So what a lot of people did was they went 0 molar here, and they went plus 1 molar here. So they were including the carbonate solid in the ice table, and they did the KSP expression with that. And I can understand why they're doing that, because they're thinking, where did those atoms go? Well, those atoms just went into that thing we call the infinite solid. It's there, and we got plenty of it, and we're not going to worry about it. Now, we can't figure out how much precipitates, because we can figure out, well, I'll tell you how much precipitates. There's going to be 0.1 moles for every liter of solution will precipitate. So I can calculate how many grams will precipitate based on this, stoichiometrically. Right? And so if I needed to know how many grams precipitated just now, figure that out, but we got to make sure we have plenty of solid there. So this is just plus S, plus 2S, plus S here. And so we got 2S and then S. And so we just figure out the KSP is going to equal the silver ion concentration squared times the carbonate ion concentration. A lot of people will forget this, because again, it's different than 16 and 17. And so this is 2s squared times s. So this is 4s cubed. S is equal to KSP divided by 4, 1/3. And so what does it come out to? Well, whatever it comes out to, then you're going to multiply it by 2 to get 2s. And then we calculate the percent that remains. Percent that remains is 2s over 0.2. Originally we started with 0.2 times 100%. And the percent that precipitates is 100. 100 is an exact number. This is an exact number, which means it has infinite sig figs minus the percent that remains. And we can figure it out. Okay. All right, other questions? Usually I like to do the math. I like to do the algebra because it's interesting to see, you know, how many different answers we get from the same problem. And this often happens on tests. You know, on tests there should be no unless you're redoing. You know, you have some kind of systematic error in pushing the buttons. That is whatever, and on your calculator, and different calculators have different orders of the way you do the operations, but you know, so it's not a bad idea to just check it and then see. But you know, this is multiple choice, so you should have the answer there. But do you? Let's see what it is, because this one I put two that were very close, 99.93 and 99.96. I did that because I wanted to see, you know, some people love to round off, you know, and their answers aren't very precise. So I wanted to see, you know.
Well, I actually got 99.87 when I did this.
You got 99.87?
And that was none of the answers.
Yeah.
So let's see what it comes out to here. What does this come out to here? The solubility.
1.2856 times 10 to the negative 4.
10 to the negative 4.
Mm-hmm.
Is that what you guys got?
Yeah.
Okay, then times 2.
Yeah, so 2.57. Sum it up with decimal sign.
2.5712.
Okay, and then do this. Percent remaining? And then percent precipitating?
That's what we got, 99.87.
99.87. Was that choice there?
No.
No? And so the answer is?
None of these.
None of these, yeah. None of these. None of them worked. I saw a lot of people wanted to do this. 100%. But when we check our K, you know, we should be checking our K. Did the K's check out here? The K's check out?
Yes.
Okay.
8.499.
Does the K check out here? If 100% of it precipitated, we get 0 and 0, which gives us a K of 0. The thing is, what is the percent error? If your calculation gives you a K of 0, and the K is supposed to be 8.5 times 10 to the minus 12, what is the percent error? The percent error is a different calculation. The percent error is your calculated minus the, divided by the times 100%. And so your percent error comes out to 100% error. Is that good? 100% error? No. So it can't be. We do this, we reset this, and then we fix it again later. In chapter 17, we reset it by just assuming, oh, we're gonna have complete reaction in one direction, and then we fix it later. So that's kind of the same, similar strategy that we had in chapter 17. All right, was that it for the questions? Well, you know, you guys have the extra time, so I can do it, but what is it, number 16? 16. So I don't want to ruin this practice test for you. You know, if you put in effort into solving it and you can figure it out, that's one thing. But if you haven't put any effort into it, then really this is kind of a spoiler. You don't want it. You don't want to listen to this. But this will be number 16. As you know, if you want just practice, you know, homework, you have the solutions manual there.
You can just give it, you don't have to solve it.
Okay. Still, what is number 16?
It says you wish to separate 0.10 molar of chloride ion and 0.10 molar of bromide ion using lead-2, and then it says parentheses, lead-2 nitrate. Show by calculation how well or how poorly the fractional precipitation of these ions would be. And then you give us the KSPs for lead-2 chloride, lead-2 bromide, yeah.
All right. Now, this particular problem, how did we do the other fractional precipitation? Did you guys, you know, what you guys should do is look at the fractional precipitation that we did in class, the one they do in the book, and then see what the difference is. How did I do it differently than the book, or did I do it the same way as the book? Did I? Okay, because I'll tell you, on this particular problem, a lot of people were just going in circles on this. But what did I do? I said, what I did was I wasted some time. I said I wouldn't have done it this way. I wouldn't have even bothered doing this calculation because it's a waste of time. But I did it anyway because last semester a whole bunch of people did it that way. A whole bunch of people did it that way. Why were they doing it? What were they thinking? Usually I just go straight to the calculation. What were the two things we need to calculate right away? No, and that's what I did. Actually, I think last semester I just went straight to the calculation, but then I figured, well, people are going down this path.
This drill is over. The exercise is over. I thank you very much.
All right. So, why were people going down this path? This is the wrong path to go down. And so, to emphasize that, that's why it went and I spent like 5 or 10 minutes going down that wrong path, just to show it's not necessary to do that calculation. Instead, what calculations do we want to do?
The solubility.
We don't want the solubility. We do not calculate the solubility in a fractional precipitation problem. What do we do?
Calculate the concentration of lead needed to precipitate both chlorine and
Yes,
bromine.
that's what we do.
Mm-hmm.
That's what we do. So maybe 10% of the class calculated solubility and then just left it. And then they did some weird calculation in which they did the solubility one minus the solubility other and then figured out some percentage. It was just way, way off. Maybe about 10% didn't even start, just fiddling around with different things. But how do I calculate how much lead is required to precipitate each ion?
So we know the amounts of chloride and bromine you have.
Yeah, it depends. So we need to know how much chloride and bromide. How much chloride was there?
0.1. And the same for bromine.
Okay, that's easy.
So then you just solve the lead.
Yeah, then we solved the KSP equation for lead, right? And
Mhm.
so I'm just gonna skip all those other steps with the derivation of this. So it's gonna be just the KSP divided by the chloride squared, right?
Yep.
And then we do this one. And then what do we do? The fractional precipitation, you just follow a series of steps. You just memorize those steps. That's the easiest. That way you won't get distracted into going and doing all kinds of other calculations. And so after I do this, then I determine which one is
Less soluble.
smaller, yeah. That's the one that's going to precipitate. And then after I do that, then what?
Then you figure out how much of the ion is left when it reaches the concentration of the more soluble.
Yeah. So how many people actually repeated the fractional precipitation problem that we did in class? Just curious. See, if nobody, this is a surprise, because if I ask the same question, like when I was at the UCSB with my class there, UCSB, you know, it's a totally different response. You know, you get a majority of students who would repeat the calculations in class. But it's not just, I guess it also depends, because did I tell you about one of the professors at UCSB who was teaching, we were talking because he was teaching a class of graduate students, chemistry major. You know, the class only had 5 students in there. Did I tell you this?
Mm-hmm.
So he spent the whole period going through a calculation he did on the board. I didn't say this?
You did.
I did. And so he said that, you know, people, this is his end conclusion, people think that by watching, they can learn it, just by watching. And it happens because everybody said it makes sense, right? It makes sense. It seems so easy. You just do this, do this, do this. So in the past, I just said, okay, we go straight to this, right? This. These are the steps in doing this. But when you sit down and do the calculation, then you realize, wow, there's so many different, you know, this is why I came up with the jungle analogy. I came up with the jungle analogy because this is what happens. You know, people watch somebody walk through the jungle, they follow them, their guide. It's so easy. I can easily find my way through the jungle because I'm following along, watching the guide following his footsteps or her footsteps. And so then when it comes to doing it by yourself, you're totally lost. And so that's what happened with these graduate students. They're totally lost. They couldn't even do. He said only one person was able to repeat it. And so, but you wouldn't expect that from grad students. But you know, the dropout rate for first year grad students is very high. You know, like my class, when I went in for grad school, half the class was gone by the second quarter, half the intern class was gone. By the end of the first year, you know, a lot. You know, we started off with a pretty big class, and just people thought, I don't want to pass. I'm tired of studying all the time, doing that, and a whole bunch of different reasons why they dropped out. So that's the reason why. The reason why I calculated solubilities was a very common error last semester. They were going down the wrong path. Why did they do that? I have no idea why they did that, because I told them what the calculations were to do. Just follow these steps, right? Just follow along with me, you'll get to the right answer. But no, they decided they're going to take this path and go and do the solubility. So I took that path, went down the solubility road and said, this is a dead end. You're not going to get anywhere with this, okay? So do not calculate solubility. So what do you do next? So we do this calculation, and then we do another calculation. The concentration is going to increase. The next calculation that we did was what? We figured out the
concentration
of chloride when, actually, which one is smaller? Did anybody do this? Okay, since nobody did this, I don't wanna spoil this one for you, because, you know, I'm just repeating myself. I'm just saying the exact same thing I said earlier just for different variables. So, you know, it'd be good to do it yourself, or at least try it yourself, since we have time. If tomorrow was a test, I'd just go through it and just explain it. But since tomorrow's not the test, why don't you go through it? And, you know, I don't do it step by step. You know, the process is, this was something I learned earlier, is I could tell somebody, step 1, do this, step 2, do this, step 3, do this. But, you know, that's just memorizing, and a lot of people, they don't necessarily memorize it unless they do it themselves. They say, okay, this is what I need to do for step 1, this is what I need to do for step 2. And so I think that's much more, you know, if you put it in your own words, rather than just copying somebody else's words, I think it's much more memorable. It sticks in your memory much better. And so, can you just look and break down the problem we did in class, and then see about applying it to this particular problem? Before I do that. The book does it a little bit differently. All right, was that it for the problems? Okay. Now, since we're going to have the test, I was thinking the other advantage is tomorrow we can do some catch up with chapter 14, which is good. So I plan to do some. So if you came in late, we're going to push the test back to Tuesday. All right, so when we graph this out, this is the crystal violet. This is crystal violet concentration versus time. We see that we get some kind of curve like this. It's not a linear decay, it's some kind of curve decay. And there are different ways we can analyze this curve. You know? What are the things we want to know about the curve? Well, we want to know the mathematics of this curve. You know, because if you have a graph like this, think about a graph takes up a lot of space, right? And how do you use a graph? We could use it like this. You know, we could plot it out, and then we can use it to either figure out the time or the concentration. In other words, we can correlate the time with concentration. But this is not the most concise definition of this graph. You know, the most concise definition of this graph is a mathematical equation. So if we can represent this whole thing, and we could reduce it into a mathematical, have you ever heard the word data reduction? Data reduction, what it means is you take this gigantic table. One way we could reduce that gigantic table is to graph it. Once we graph it, we could further reduce that, because if we could represent, like, say for example, if we had a straight line like this, what's the most concise, the least space required way of showing everything in this plot? It would just be this. We would reduce this whole thing into one simple equation, y equals mx plus b. And then we have everything. We don't even need the plot. Right? And so we want to do the same thing here. We want to reduce this into some mathematical equation that we can use to calculate whatever. We could calculate concentration, we could calculate the time, etc. Now, this could be mathematical equation or equations. Now, we're going to do a funky equation here, you know, because essentially we just want the equation of this that tells us. And so the first equation is going to look a bit bizarre, but this is just the what's observed by looking at a lot of these plots. The first equation that we get isn't a direct equation for the line. fit this, what kind of mathematical function does this look like, you know? Logarithmic or exponential, right? Well, you know, this first equation isn't a direct. This first equation is an equation for the slopes. There's a pattern in the slopes of this. And the slopes are the slopes of the tangent. We call those the instantaneous rates, the slopes. And so the first equation is this pattern in the slopes, which isn't terribly obvious. I mean, if you looked at this and you said, okay, I see the mathematical equation. Do you see a mathematical equation that the slopes fit right now? Or some kind of mathematical formula that you can put the slopes on? And the pattern in the slopes, this would be of the tangent lines. Which we call the instantaneous rates. That is the slope or the instantaneous rate at any time t. And so this pattern is going to be delta CV plus over delta t. That's the slope. And the slope can be determined. Well, this is going to be absolute value. This slope can be determined by this. Now, this is the mathematical function that fits it. There's going to be a constant, which we call little k. That's a constant. And this constant is named the rate constant. You just get from graph. And then it's going to depend on the crystal violet concentration. Because what happens is, as the crystal violet concentration decreases, what happens to the slope or the rate? The rate also decreases. So as the crystal violet concentration decreases, the rate decreases, but it's going to decrease by amount proportional to k here, you know, because we're going to multiply k times the crystal violet. But the rate of decrease is nonlinear, and so the rate of decrease might be linear. And so what we do is we put a term here, m, like this. And then it's also going to depend on the hydroxide, because as the crystal violet concentration goes down, what happens to the hydroxide concentration? It also goes down. As the hydroxide ion concentration decreases, what do you expect to happen to the rate? Rate probably decreases as well. So even though we didn't plot out the hydroxide here, the hydroxide is going to have the same kind of pattern here. And so the hydroxide concentration is also going to impact the rate. But it might not impact it in the same way that crystal violet impacts it, and so we put an N here. And so it turns out that the rate, or the instantaneous slope at any time here, is going to depend on K times the crystal violet concentration raised to some power M times the hydroxide ion concentration raised to some power N. Okay, and here it turns out that this is going to equal the change in the hydroxide. So if we measure the pH and watched how it changed with time, we could make a plot with the hydroxide showing the same type of deal.
What is that? Right next to the hydroxide, the delta hydroxide at the very top. Oh.
It's a smudge.
Is that also in absolute value terms?
Yeah. Except this is going to be positive, so you don't really need to do the absolute value. So sometimes they'll leave the absolute value signs off. Or no, this is going to be negative, so you do need the absolute value, sorry. Which is going to equal the rate of crystal violet hydroxide production over time, which this would be positive. So we don't need the absolute value here. This thing is called the rate law, this mathematical equation. Now you go, how the heck was this determined? Well, yeah, a lot of people looked at a lot of graphs and a lot of slopes and figured out, oh, this is the pattern that we see in how the slope changes with concentration. This is slopes changing with concentration, not with time. And so it's kind of funny. And so what we can do is we can extend this to this. We extend it to some generic reaction, AA plus BB plus ... This is going to go to products. whatever the products are. Actually, should we do it this way? Yeah, we're gonna do it this way. And so the rate is equal to 1 over A times delta A over delta T. Depends on the coefficient here. You know, so this is normalized rate. And so let's say if it were 1A plus 2B, then 2B has to react twice as fast as A. Otherwise the stoichiometry doesn't hold. So we normalize it. 2B must react 2 times as fast. 2 times as fast as A. So we do this, which is going to equal, this would be absolute value, 1 over B, delta B, over delta T, etc. And this is going to equal K, the rate constant, times the concentration of A raised to the n power, concentration of B raised to the n power, dot, dot, dot. Now, K is the rate constant, M is called the order with respect to the concentration of A, N is the order with respect to the concentration of B, and then we just continue. O would be C, etc. We have the overall order of reaction, overall order of reaction equals just M plus N plus dot, dot, dot.
Chemistry contractions.
Now, where do we get M and M? How are these determined? Determined. There are a number of ways of determining it. Basically, we're going to get these from the first part of the chapter. We're going to get these from experiment, not from the equation. Let me put a little asterisk there. Later on, these are not from equation. Let's put this little asterisk. In the second half of this chapter, we can get these from theory. We can determine M and N, etc. from theory. And so the first part, we're just going to learn how do we get M and N from experiment. Probably the simplest experiment, the easiest way of doing this, or one of the easiest, is something called the method of initial rates. So let's do a generic reaction before we go back to crystal violet. And so in this example, let's do A plus 2B yields product. And the first thing I want to do is I want to figure out how the rate varies with the concentration of A and the concentration of B. That's going to be given by the rate law. The rate is equal to K, which is the rate constant, times A times B. Here, I'm tempted to put squared here on B, but it's not squared. We don't know. It's just M and N. And so N is not equal to the coefficient here necessarily. It might be, it might not be. We don't know. K we can also determine from experiment as well, once we have M and N. So this is how we determine it. essentially. We do a series of experiments. By setting up a table like this. And so we look at the concentration of A, the concentration of B, and how that impacts the initial rate. We have to do the initial rate here because the rate is always changing. And so this would be the rate at these initial concentrations. And as the concentrations change, the rate would change. And so, you know, we have to figure out where are we going to measure the rate? Well, the easiest place to measure the rate is, you know, right at the beginning, because we know what the concentrations are right at the beginning. Otherwise, we have to do an experiment to determine what the concentrations are, which is a hassle in the middle of it. And so here it's easiest because let's say I have A initial and B initial here, which we'll call it 1. A1 and B1. And this is for experiment 1. Trial 1. And then I got rate of 1 here. And then in the method of initial rates, what we'll do is we'll do this. We're going to double this. So we'll go 2 times. So here we're going to have 2 times A1. This is going to equal A2. And then here we're going to keep B1 the same. We won't change that. And so what we did was we doubled A. And then what we see is what happens to the rate. And so, well, rate 1 is equal to Ka1 B1. Okay, and this is to the m power, this is the n power. Rate 2 is equal to K, okay, well, A2 to the m, B2 to the n. And so let's say I do this and I measure the initial rate, or I calculate the initial rate, or whatever. I determine the initial rate, and let's say the rate doubled. Let's say it's 2 times R1, its rate. And so the rate doubled. And so what that means is, it means this, that this is going to equal K. Now A2 is 2 times A1. And this whole thing is raised to the nth power times B. B2 is the same thing as B1 because I didn't change it. It's the same concentration, so that's equal to n. This is equal to 2, or 1. And so separating this out then, I get this. I'm going to factor out the 2, so I get 2 to the m times Ka1 to the m, B1 to the n is equal to 2R1. And so this is R1 here. You see, R1 is equal to this, so this and this cancel each other out. So I get 2 to the m is equal to 2, therefore n is equal to 1.
Wait, how did that cancel?
Oh, because I have this. So I just substitute. So here, R1, substitute this in for R1, they cancel. Or this, substitute R1 here, will cancel. But then I have to run one more experiment. Experiment 3, let's keep A1 the same, but let's double B. And so here I go 2 times B1. So we're going to keep A the same as A1. So this is equal to A at trial 3. This is equal to B for trial 3. And then let's see what happens. So if I do this, this is what I'm going to observe here. for B. B, rate of 3, let's say we measure it. When we measure the rate for 3, let's say it comes out 2 times the rate of 1. So if I measure the rate of 3, it comes out 2 times rate of 1, then this is what it means here. I can go through the same thing like this, but let's look at alternative way. I'm going to skip the math here and then just look at it. So far, this is our rate law. The rate is equal to Ka. Now the power here we just determined, it's got to be the first power. So what we say is it's first order in A. And then B to the mth. And so this is what I think. Okay, as far as this goes, A is first order, and then what I'm going to do is I'm going to think about doing this. I'm going to go N times the concentration of B to the mth.
Is that H or K?
Is that H or K? Yeah.
Okay, this is supposed to be K. Sorry.
Okay, Professor, and that's 8 to the 1 for the first one, the first row.
Yeah. Yeah. Right. Okay, so I do this, and then I'm going to get this. This is going to be B to the m, n. And so what I'm going to do is I'm going to go n times B1 here for this. And so I just have some kind of reference at the beginning. So here's my B1. If I go, let's say I double B1. If I double B1, I have different things that can happen. One, if I double B1, nothing happens to the rate. Well, if I double B1 and nothing happens to the rate, then n must be 0, because it doesn't have any impact. And so that, I shouldn't have used n here. Let's use a different one. This should be n, sorry. L, M, n. So let's use x here. So if I double it, then the impact is, if I double, that's x to the n, and nothing happens to the rate, then n must be 0. If I double x and the rate doubles, then n must be 1. If I double x here, that is, I make x 2, and the rate quadruples, then n must be 2, because it would be 2 squared, right? If I double x and the rate goes up 8-fold, then n must be 3, because it would be 2 cubed. Does that make sense? And so this is the alternate way of doing it. And so what I see is that what happened is if I double B here and the rate doubled, then n must be equal to 1. And so it's going to be first order in A and first order in B. And so actually I'm making this much more complicated than it is. It's actually quite easy, because most of these you can just do in your head. And so the rate so far is going to equal K. It's going to be A to the first, B to the first. And so we say it's first order in A and first order in B. So if I double A, the rate doubles. If I double B, the rate doubles. What happens if I double both A and B? If I double A and double B, the rate would go up 4-fold. The rate would quadruple. And so if I double both, then we're looking at the overall order. And so what we say is this is first order in A, first order in B, and second order overall. So let's take a look at some sample problems from the book, and then see if we could just figure those out.
Why did that first step
for here.
Yeah.
It's not step 2, this is trial number 2.
Okay.
So I do 3 separate experiments, each with a different set of initial concentrations. The reason why is I chose it to be the same. So in the method of initial rates, what you do is you change one, leave the other one the same, so we can see the impact. Because this one, the concentration didn't change, therefore it's not going to have any impact on the rate. If the concentration is the same, the rate should be the same. This one, we changed the concentration on A, and therefore that's what happened there. And so what we want to do is, oops, is it time? Yeah, shoot. I thought I had more time, but I don't. So we'll continue this tomorrow.